UVB, a small amount of it from the sun reaches the earth, but most of it gets destroyed or absorbed in the stratosphere by ozone. And then UVC, it's completely absorbed in the stratosphere by both ozone and oxygen. And if it wasn't, there wouldn't be very much life on Earth at all, because that dangerous radiation would definitely kill most mammals, including us, on the planet. So take a minute to answer questions 1 and 2 for section 3.4. So take about 5 minutes. You can go into your group rooms and answer these with your group members. And then at 11:35, return to the general room and we'll resume our notes. Yes, Gabrielle?
I didn't mean to do that.
Okay. So we talked about their relationships with each other as far as frequency and energy and wavelength are concerned. UVA has the longest wavelength. UVC has the shortest wavelength, and UVB falls in the middle. And as far as frequency and energy, they're the opposite of wavelength. UVA has the shortest frequency and smallest energy, whereas UVC has the highest frequency and highest energy. And UVB falls in the middle. But what about potential for biological damage? Which type is the most dangerous? And so we would say the most dangerous type of UV has the highest energy. The greater the energy of the radiation, the greater potential for that radiation to damage your DNA. And when your DNA gets damaged, which we also call mutated, that opens the door for cancer. And so the one that has the greatest potential for biological damage is going to be the one with the highest energy. And therefore, that would be the UVC. And so, because it doesn't reach the earth, then we are protected from it. But if we didn't have the ozone layer in the stratosphere protecting us, then it would reach the earth. And therefore, we would see big increases in skin cancer, which we did see around the world, including in our own country, in the 70s, into the 80s, when we were damaging our ozone layer and therefore depleting the ozone in our stratosphere. And we'll talk more about that later in the chapter and what things that we've done since the 80s to try to repair what we call the hole in the ozone layer. What about question 2? How would you go about answering that question? You would want to calculate the energy for each of these wavelengths. UVC has a wavelength of about 242 nanometers, UVA 320 nanometers. So you would want to calculate the energy and then for each of these, and then subtract the lower energy one from the higher energy one to get the difference between the two. So calculate the energy for both using this equation. And so to be being prepared for class, make sure you have your calculator with you at the beginning of each class meeting and that you are ready to work problems. Some of our questions don't require calculation, but a lot of them will that we do in class. And so I expect you to be doing the problems in class. So definitely have your calculator ready, or your calculator app. If you use an app or an online calculator, have that up and ready. So what's the energy of the 242 nanometer photon? Anyone have an answer? We did a similar problem to this in class on Monday. And it's very important after each class meeting that you go back home and go back while you're at home. I'm still in the old-fashioned mode of thinking that you go back over your notes, because we did a problem just like this on Monday. Am I finished with this problem, or is there one more step that I need to do? What else do I need to do? Can I cancel this meter with the nanometer? I see that my seconds canceled. I'm calculating energy, and we said Monday that the energy unit is the joule. But I need to cancel these length units. But I can't cancel a meter with a nanometer, so what do I need to do? What we learned to do in chapter 1, conversion of units.
They all have to be the same unit.
So I need to use a conversion factor here, don't I? In order to cancel meter and nanometer, I've got to use the conversion factor for converting a meter to a nanometer. Because I've got meters here in the numerator, to cancel it, I'm going to need a meter here in the conversion factor's denominator. Because I've got nanometer here, it's in the denominator of my formula or equation. Then to cancel that nanometer in my conversion factor, I've got to have nanometer in the numerator. And so therefore now I've got to put the conversion factor numbers that go with those units. For every 1 nanometer, there is 1 times 10 to the negative 9 meters. So now my meter is canceling. Thank you, Tessa. And now my nanometer also cancels. So now I'm ready to calculate my answer. I multiply my numerators together. I put that in a fraction in the numerator. I multiply my denominators together. Then I put that result in the denominator. And then I do my final calculation of division. Or if you're comfortable, you can do the calculation on your calculator in one step. And by using your store functions. It just depends on how comfortable you are in doing the calculation. If you feel you need to do it in multiple steps, then absolutely do that. So the energy for the 242 nanometer photon for UVC is 8.21 times 10 to the negative 19 joules. And so for the 320 nanometer UVA, I'm doing the same calculation. I'm just replacing 242 with 320. And so for the 320 nanometer UVA photon, we get 6.21 times 10 to the negative 19 joules. So the difference, or in energy, which I call delta E, and so the difference is 2 times 10 to the negative 19 joules. And so that brings us to the end of part 1 of our notes. Part 1 focused heavily on the relationships between wavelength, frequency, and energy of light, which we call packets of energy called photons. We've also now talked about 3 different types of UV radiation. And so now let's continue our conversation of UV radiation and look deeper into the biological effects of UV radiation. And so we said that UVA radiation, it is not absorbed in the atmosphere. It reaches the Earth. But UVB and UVC radiations, UVB, some of it gets absorbed in the atmosphere, and UVC, all of it gets absorbed in the atmosphere. UVB and UVC types of UV radiation, they have enough energy to cause some molecular bonds to break, whereas UVA is not energetic enough to break molecular bonds. So that's why all of it reaches the surface of the Earth. But UVB and UVC have energies that are strong enough to break the molecular bonds in 2 particular molecules, oxygen and ozone. And UVC can break oxygen bonds and ozone bonds, whereas UVB can only break ozone. UVB is not energetic enough to break oxygen bonds. And so I want you to think about that. Why can't UVB break apart the bonds that are holding an oxygen molecule together, but it can break apart the bonds holding an ozone molecule together? We're going to learn how to draw what are called the Lewis structures of each of these 2 molecules, O2 and O3. And then once we learn how to draw the Lewis structures, then we'll better understand why UVB is not strong enough to break the bonds in O2, but it can break apart the bonds holding O3 together. So what we have here are these circles representing oxygen atoms, and the springs holding those oxygen atoms together represents the molecular bonds. Molecular bonds are also called covalent bonds. And so UV light will hit the bond, and it's going to first cause it to vibrate. So when that bond absorbs the UV light, it's going to first start vibrating, and its vibrations are going to be so strong that it's going to cause the bond to break. And so this here is 3 oxygen atoms connected. So that is ozone. And both UVB and UVC are strong enough to break the bonds in ozone. And so when we overexpose ourselves to sunlight, which of course contains UV light, that UV radiation will get absorbed by our skin. And so UVA, all of it reaches the Earth because this energy is not strong enough to break bonds in ozone, nor oxygen. And so when that UVA reaches the Earth, it can penetrate your skin, and it's going to therefore be able to remove electrons from molecules like water in your skin. And when it does this, it creates species known as free radicals and other reactive oxygen species, because oxygen is a part of water. Now, most of the UVB is absorbed by ozone in the atmosphere, but UVB is not strong enough to break the bonds and therefore be absorbed by oxygen. So some of the UVB actually makes it to the Earth's surface. UVB is higher in energy than UVA. And so therefore UVB can cause some of the chemical bonds in your DNA to break when it hits your skin. So therefore DNA molecules can be damaged by absorbing this UVB radiation. And also UVB can remove electrons from water molecules just like UVA does, and therefore create these dangerous free radicals. So whenever this damage to your skin happens, your body will naturally release a compound called melanin. And melanin is a dark pigmented chemical. So that's what causes the dark splotches on your skin when you're overexposed to the sun, is due to the release of this dark pigmented chemical called melanin. And if the damage is not repaired by your body's built-in DNA repair mechanisms, then what can happen next is skin cancer. So our bodies do have built-in DNA repair mechanisms, but some damage caused by overexposure to the sun, if that damage does not get repaired, that DNA damage does not get repaired, then that could be a precursor to cancer. And so UVA radiation has a longer wavelength than UVB. So UVA can penetrate 3 different layers of your skin. The top layer, which is the epidermis, and then the layer underneath that is the dermis. And then what you get to as you go even deeper into the layers of the skin is the subcutaneous layer. So UVA can penetrate through all of those layers of the skin. UVB, however, with a shorter wavelength, will only penetrate to your epidermis. But UVB is higher in energy. And by being higher in energy, it can create free radicals by removing electrons from molecules like water, and it can damage DNA directly due to that high energy. UVA, it can only create the free radicals. And those free radicals can then go on and react with other molecules like DNA and therefore cause mutations. But the UVB can damage DNA directly by breaking bonds in DNA because it has strong enough energy to break DNA bonds directly. The UVA is not strong enough in energy to break bonds in DNA directly, but it can remove electrons from water molecules in your skin and therefore create these free radicals. And then these free radicals that are created can go on and react with your DNA and therefore mutate your DNA. But one answer to preventing this from happening, can anyone think of a way to take preventative action against UVA radiation, removing electrons from your water molecules in your skin, creating free radicals, and then those free radicals going on to damage your DNA?
Doesn't iodine protect against that?
Repeat that.
Doesn't iodine prevent?
So you kind of faded out there. But I think what you were getting at is you can do things with your diet to get rid of the free radicals. Iodine, I'm not sure about iodine being one of those preventative measures. I'll have to look that up. I've never heard of iodine. But just eating a diet high in antioxidants. What antioxidant compounds do is they get rid of free radicals. So if you've got antioxidants high in your blood, in your body already, then when those free radicals are formed, they are destroyed. So does anyone know what foods are very high in antioxidants? Your dark
Blueberries?
Yes, your berries. Yes, your dark fruits and vegetables. You know, your purple fruits and vegetables, your dark red fruits and vegetables like berries, and also fish. Those are the two main types of foods. So basically, any dark fruits or vegetables would be good things to make sure that you have plenty of in your diet, because those foods have high antioxidant levels of nutrients in them, and they will destroy those free radicals. So that is one remedy to protect yourself from potential damage to your DNA caused by UVA radiation. But as far as UVB radiation is high enough in energy that it can just damage your DNA directly without going through the free radical route. So therefore, the only thing to protect yourself against UVB is just to not to overexpose yourself to the sun by wearing your protective clothing, wearing your sunglasses, so on and so forth. But as far as UVA radiation, that can be alleviated by having a diet high in antioxidants. And so here we have a summary of the three different types. And UVC gets absorbed completely by O2 and O3. UVB, some of it does reach the earth, and your skin rapidly absorbs it, but some of it is absorbed in the ozone layer by O3. UVA is not absorbed at all in the atmosphere, but it's not as energetic as UVB, but it is longer in wavelength, so it can penetrate through all three layers of your skin. But having a high, rich antioxidant diet can help protect you from the potential danger of UVA. And so the facts about skin cancer, we all have heard that we get vitamin D from the sun, so some sun is good for you. That is true. but too much exposure can lead to cancers and eye disease. So therefore, you can have a diet that's high in vitamin D and therefore limit the amount of sun exposure for the purpose of getting vitamin D. Lots of foods like milks and juices and things of that nature are fortified with vitamin D. And also vegetables like broccoli and other vegetables are also high in vitamin D. So you can get your vitamin D from your diet instead of the sun. Because when you weigh the benefits of the sun, vitamin D, versus the danger, and if you can get vitamin D from another source, then that's the better way to go. Because most skin cancers are linked to exposure to sunlight. So getting your vitamin D from your food is the better way to go. Skin cancer can develop at any age, but it's more common in older people. They've been being exposed to sunlight for more years than a younger person, so that makes sense. Skin cancer may not develop immediately. It may take years after repeated excessive exposure to happen. And even after excessive exposure has been stopped for a few years, the skin cancer can still pop up. So that's one thing to be aware of. UVA in the sunlight at the Earth's surface is most strongly linked with skin cancers. So UVA is the main culprit for skin cancer because it can penetrate all 3 layers of your skin. But it is believed that UVB does play a role because a small amount of it does reach the Earth's surface. And so when weighing your personal exposure to radiation, if you don't get enough vitamin D, you can have bone problems and therefore skeletal diseases, and you can have vitamin D insufficiency. But if you get too much exposure to the sun, you can have skin cancers and eye diseases. So therefore, you want to make sure you have a good balance of as far as how much exposure that you are submitting yourself to the sun. And so you want to lower your disease burden by getting enough vitamin D, and if possible, get it from different sources than the sun, and never overexposing yourself to excessive sunlight. And so how would you know if it's a day outside that puts you at a greater risk for UV dangers than other days? The weather forecast also will give you daily a UV index forecast. And that forecast is color-coded. It's a color-coded UV index scale. And it's used to predict the risk of sunburn from overexposure to the sun. And so some important factors that will affect whether or not you have a high risk or a low risk for sunburn on a given day are things such as what is the concentration of ozone in the upper atmosphere. The higher the concentration of ozone, the lower your risk, because the higher the concentration of ozone, the more of the UVB that is going to be absorbed up there, and less of it will reach the earth down here where we live. Other things are elevation. If you're at a higher altitude and closer to the sun, you have a greater risk of sunburn. And then also cloud cover. Cloud cover will also reduce the intensity of the radiation coming in from the sun. And so they have the low, moderate, high, very high, and extreme categories. And then they give specific number ranges for each index. So if the index is between 0 and 2, you have a very low exposure category. If you're a person that burns easily, it's still advised to cover up and use sunscreen on a low exposure day. And the number index ranges all the way from 0 to 11 plus. If we're in the 11 plus range, that's extreme. Take full precautions against sunburn, namely stay indoors, because if your skin is unprotected, it can burn in minutes. And then the highest sun risk in any given day is between 10 a.m. and 4 p.m. So on these high to very high to extreme UV index days, it's best to stay indoors between 10 and 4. Moderate days, 3 to 5, stay in the shade when the sun rays are the strongest between 10 and 4, if possible. But no matter what the index is, it is advised to cover up as much as your skin as possible and use sunscreen. And so we talked about how the ozone layer of the stratosphere protects us from the most dangerous UV radiation, UVC. And so we've seen this picture before of the different regions of the atmosphere. We live in the troposphere. The troposphere is everything between 0 and 5 kilometers above the surface of the Earth, all the way to 15 kilometers. When you start getting above 5 kilometers above the surface, that's your higher elevations, like Mount Everest is about 8 kilometers above the surface of the Earth. Jet airplanes, they fly at about 12 kilometers or so above the surface of the Earth. Once you get beyond 15 kilometers from the surface of the Earth, now you're in the stratosphere layer. So the stratosphere ranges from 15 kilometers, which is 9.3 miles, all the way to 50 kilometers or 31 miles. The ozone layer itself is between 15 and about 30 kilometers above the surface of the Earth. And the ozone layer of the stratosphere is where your storms form. It's also where weather balloons fly and orbit the Earth. And so this ozone layer part of the stratosphere is the lowest layer of the stratosphere. And it's here where you have the highest ozone concentrations of all the different layers of the atmosphere, from the troposphere, stratosphere, mesosphere, so on and so forth. The highest concentration of ozone is going to be in the stratosphere, and in particular, the ozone layer part of the stratosphere. And that's the area of the stratosphere that protects us the most from dangerous UV radiations. The UVC gets completely absorbed here, and most of the UVB gets absorbed in this area of the stratosphere. So some things that we want to note: as your altitude increases, the atmospheric pressure decreases. And as you go to higher and higher elevations, there are fewer air molecules available. So therefore, the higher above the surface of the Earth you go, the amount of air decreases, and it gets harder to breathe. You can get headaches. You can tire more easily. So if you're climbing Mount Everest, as you go higher and higher, you're going to have less and less oxygen available because you have less and less air available. And the higher your elevation, the lower the boiling point temperature of water is. So therefore, on Mount Everest, water will boil at a much lower temperature than it will boil in Miami. And in Miami, at sea level, it's going to boil at 100 degrees Celsius. On top of Mount Everest, it may boil at 80 degrees Celsius. And so our ozone layer is that bottom part of the stratosphere where we have maximum ozone concentration. The ozone concentration in the ozone layer in the stratosphere is about 12,000 parts per billion. Whereas in the troposphere, which is where we live, That's the surface of the Earth. From the surface of the Earth up until about 15 kilometers or so above the surface, that's where you're going to have only about 20 to 100 parts per billion of ozone. And this comes from mainly air pollution. Due to automobiles. So that's why we do have some ozone in the troposphere, and it's put there by human activities. And therefore, in the troposphere, ozone is an air pollutant. But in the stratosphere, it protects us. It keeps us alive because it prevents dangerous UVC and most of the dangerous UVB from entering the troposphere. And so the difference between oxygen and ozone is their chemical formulas: O2, oxygen; O3, ozone. And then we see the different particulate level representations, symbolic representations, and then the particulate representation, each red circle representing an oxygen molecule. And with them being in close contact, is showing you that they're bonded. There's a chemical bond, and in particular, there's a molecular or covalent bond or bonds holding these oxygen atoms together. So, where did ozone come from? Well, ozone's been in our atmosphere since our atmosphere formed. And the way ozone was created is by weather. So whenever there's storms, there's always thunder and lightning. Lightning is electricity. And of course, energy gets released whenever there is lightning. And so that energy from lightning serves as a catalyst and causes the oxygen molecules to be converted to ozone. So for every 3 oxygen molecules that get converted, 2 ozone molecules are created. So the bonds that are holding the oxygen molecules together, those bonds get broken. Those atoms of oxygen are now free to rearrange to form O3 molecules. And it's the energy provided from the lightning that allows those bonds to be broken, and therefore those atoms having the opportunity to rearrange. And so here in this picture, we can see that the ozone concentration is at its highest at an altitude of about 23 kilometers above the surface of the Earth. And that's going to be our typical ozone layer center, the center of the ozone layer. So at the center of the ozone layer is where you're going to have the highest peak concentration of ozone. In the troposphere, we see ozone will increase with increased air pollution. So we have much lower levels of ozone in the troposphere, and the amounts of ozone that are present in the troposphere are due to air pollution. And as air pollution increases, so does the ozone concentration in the troposphere. And the way ozone concentration is measured, it was formulated by a scientist last name Dobson. And so they're called Dobson units, DU. And so the concentration of ozone is related to compressing ozone at 0 degrees Celsius to form a 3 millimeter thick slab of ozone with a pressure of 1 atmosphere. So 300 Dobson units is therefore equivalent to 3 millimeter thick slab of ozone. And that's going to be relative. So 100 Dobson units is going to be equivalent to a 1 millimeter thick slab of ozone. 500 Dobson units would therefore be equivalent to a 5 millimeter thick slab of ozone, so on and so forth. And so most climatologists or atmospheric scientists or chemists, they will measure the concentration of ozone in Dobson units. And so before we meet on Monday, I want you to take a look at these questions for sections 3.5 and 3.7 of chapter 3 that we've just gone over, and answer questions 1 through 4 before coming to class on Monday. Also this weekend, you should definitely read chapter 3. I expect you to have chapter 3 read pretty much in its entirety before our next class meeting. And if not in its entirety, at least through section 8. Because after we go over these questions from sections 3.5 through 3.7, we're going to get into section 3.8, which covers Lewis structures. And I want you to have some idea about Lewis structures and the rules for drawing Lewis structures. Go over these rules prior to class on Monday. And then we're going to talk about Lewis structures. We're going to practice drawing Lewis structures on Monday. So if there aren't any questions, we'll go ahead and end class for today. If you have some questions, feel free to hang around after class and ask me whatever questions you have. Just a reminder that the bonus opportunity to add some points onto your first exam score, that bonus assessment will be available until Friday night at 11:59 p.m. To access it, go to eLearn, click on the Activities tab, and then click Assessments, and then you'll see the Limiting Reactant bonus assessment. There's a short 5 or 6 minute video you need to watch first. And then after you watch the video, you should be ready to answer those questions. And the questions that you are asked are very similar to our chapter 2 notes, part 3, determining theoretical yield, limiting reactant for the synthesis of aspirin. We went through these types of questions and calculations in class last week. And so the questions that are asked on the bonus assessment are very similar to questions 1 through 6 of the notes for chapter 2, part 3 notes. So definitely review the notes, then watch the video before answering those bonus questions. And again, that bonus assessment is available until Friday night. So have a good rest of your Wednesday if you don't have any other questions for me. And I will see you in lab tomorrow or Friday if you have me for lab, or I'll see you on Monday in class.
I had a question.
Absolutely.
What did you say about watching a video?